I'm like super excited to be here talking to you today about tracking aircraft using NERVs and Phoenix. You can do this in real time using a radio protocol. It's known as Automatic Dependent Surveillance Broadcast, also known as ADSB. I've heard some people call it ADSB. Well, real quick, we'll just get the housekeeping stuff out of the way. Again, my name is Jeff Smith. I'm from Oklahoma City, so go Thunder. It's too bad Seattle doesn't have an NBA team. I don't know, maybe someday they'll get one. Sorry. I blame Kevin Durant. Anyway, all right, so I've started writing code in 1996. Hard to believe that was 21 years ago, but I guess that means my code can legally drink now. I flirted with Erlang for a couple years, picked up Elixir spring of 2014. I think it was just after 0.13 release, maybe. And I'm proud to be on the fulfillment engineering team at Latote. Yay. Solving some really interesting and challenging item tracking and warehouse management problems there. So stop by our booth and say hi. Previously, I was with Ultimate Software in Florida, a startup named Ossium. I also, being from Oklahoma, had to do a little bit of oil and gas at Chesapeake Energy. And I recently joined the NERVs core team. Pretty cool. I love space and astronomy, anything related to STEM, hockey, and I really like waffles. You can find me on GitHub and Twitter. Thank you. At Electric Shaman, and then on the Elixir Slack is Jeff Smith. So all of the code that I'm going to be talking about today is, you can find that here on GitHub. And squitter is kind of a weird word, but if you can't remember that one, then a tiny URL, elixir-aircraft will point to the same thing. All right, so why would someone want to track aircraft? This is not something that requires like a license or thousands of dollars worth of equipment to do. At minimum, you can get started with like about a $25 software-defined radio dongle on Amazon. And occasionally when I talk to people about this, they get this really kind of nervous look in their eye, like Bruce just did. Like they're thinking, surely you can't be serious. But of course, I am serious. And don't call me Shirley. Sorry. I'm not sure if that look on their face is just because they're surprised doing this is easy and legal, or they're just surprised that like I'm actually that geeky. But I personally find all this stuff fascinating, and here's some reasons to consider why you might too. It's a really great way to learn about the operational aspects of aviation. There's a lot of weird words and things that happen, like in SIGMETs and AirMets and all kinds of strange stuff. And if you don't know what any of that means, then that's kind of my point. I still have to learn about it every day. It's a really great host project for learning about RF, which is kind of a black magic, especially when you can do really interesting things with software-defined radio. You can experiment with simple DIY antennas. You can also impress your friends and coworkers and scare your neighbors. Like this time, this is a couple weeks ago, I said, does anyone know why the Oklahoma City police chopper has been coming out this way and doing donuts in the sky for the last 2 weeks or so? I've seen them 6 or 7 times, and it was like crickets. They're like, what's that guy talking about? Oh, also, you can get a free FlightAware enterprise account if you send them your data. This is how they fill in the gaps between air traffic control centers. And that gets you, a little bit of extra information. If you go to their website, you can see things that aren't normally part of their tracking system, the public tracking system, like AirMets and SIGMETs and turbulence reports and all kinds of stuff. Also, you can see position-only flights, which are considered flights that don't have a flight plan, such as the time that Con Air flew over my house, and all I saw was a call sign that was DOJ. Looked it up on FlightAware's site, and turned out it was United States Department of Justice Prisoner and Alien Transportation Service. All right. So what is ADSB? Again, it stands for Automatic Dependent Surveillance Broadcast. It's basically the GPS-based successor to the secondary radar surveillance system, part of the next generation FAA program. This is something they're making mandatory, the ADSB out part of it in 2020. The ADSB in part, which is basically what I'm doing by receiving ADSB, that's the other part of it. It's essentially a high-rate broadcast of operational data by the aircraft, and this is going to be on 1090 megahertz, sometimes also known as 1090 ES, because there is a second counterpart to 1090 on 978 megahertz. It's called UAT. It stands for Universal Access Transceiver, and that's a really interesting link too that I haven't gotten into. But for the purpose of this talk, we'll just be talking about 1090 ES. So it's message-based. There are different types of messages, and they're all encoded by a type code value. One thing I should mention, it confuses kind of a lot of people when I show them these really awesome maps of airplanes that are like 200 miles away, is that 1090 megahertz is line of sight. And so if you're in your house and trying to pick up something like I was, much like I was yesterday in the hotel room, and getting like one plane every 2 hours, don't be discouraged. If you just take the thing outside, and you'll probably get a lot more. But it does factor into some things whenever your range will basically be decreased within the house. All right, so what kind of messages are we talking about? These are the primary three that I would consider for tracking. There are some other message types, but these are probably the most interesting ones. There's the aircraft identification. The aircraft will broadcast this about one time every 5 seconds on average. Airborne position, this is one that's broadcast twice a second. Identification contains the call sign and the category, and that category is it categorizes the aircraft's wake turbulence or vortex or whatever they call it. Position message will give you the altitude, the latitude, and the longitude. And then there's the airborne velocity message, which will give you the heading, airspeed, and vertical rate. So this is what the message structure looks like. This is a legacy structure which is backwards compatible with something called Mode S. Mode S is used in the secondary surveillance radar system that's intended to be succeeded by ADSB. The format is the first field. It's 5 bits. For ADSB, this is going to always be a value of 17. Capability comes next. That's 3 bits. That basically tells you what type of transponder is in the aircraft, what type of features does it support. It's kind of like a version, I guess you could say. The third field is a really important field. It's called address. This is a field that is 24 bits long. It's also regulated by an international organization known as the ICAO, and they dole these out kind of like, I guess it's kind of like MAC addresses where there's a certain prefix or range that they allocate them in an organized way, and certain countries have like certain ranges, and you can actually use that to figure out like where the aircraft is registered. But this is the unique key. This is I guess you could say it's a primary key for the aircraft. It's tied intimately to its registration. So for a lot of aircraft, this will remain the same value for the lifetime of that aircraft. It's going to be really important when I get into some of the later parts of this talk. Payload, this is obviously the good stuff. It's 56 bits, so it's not a lot. For ADSB, everything is going to start with the type code. And I'll show you an example of that in a second. And then finally, we have parity. We have 24 bits of parity. And this will allow you to verify that the message that was sent is the message that is being received. It will also allow you to correct, I think, up to 1 bit of error. And then just below, I thought, I'm a huge fanboy of the binary pattern matching stuff. I think it's even taught me more about just parsing data than I ever knew when I tried to do it in C with bit shifting and stuff. But this is an example of how easy it would be to basically isolate these fields and parse them out with binary pattern matching. Oh yeah, I meant to go through these one by one, sorry. So here we see the address. This is typically the address is represented in hex. When you see it on my app and other apps, you'll see this represented as a 6-character hex value. Then this is an example of an aircraft identification message. You can see, hopefully you can see, the first field has a value of 4, which means this is, in fact, an aircraft identification message. Lets us know how to parse the remainder of the payload. Next comes category. In this case, we have a 0, means this aircraft is not presenting any category information. The remaining fields in this particular message are all 6-bit character codes. There are 8 of them. In this specific example, it decodes to KLM 2013 and then an underscore for padding. And then parity. All right, so how do we actually get these messages out of thin air? This is the world's fastest SDR tutorial. Basically, software-defined radio dongle you can buy on Amazon will turn radio waves into stuff that looks more familiar to us. Essentially what's going on here is the radio has an analog to digital converter in it. It quantizes the radio signal into basically amplitude and phase. And it's according to basically a center frequency that we give it and a sample rate. So sample rate tells it like at what interval to quantize it. This data gets sent over a stream via USB, and then software-based digital signal processing algorithms can demodulate the original signal. All right. So now that we're all experts on SDR, we kind of explore why I thought it seems like Elixir would be a good fit for this type of application. There's some really interesting kind of parallels. They map, I think, quite well to features in our language platform. First of all, at any given time, there's probably like 5,000 aircraft flying over the United States. Peak traffic that can be closer to 10,000. So obviously, if we're talking about receiving this stuff, we need to have concurrency, and that's obviously the bread and butter of the beam. Second of all, we're tracking state per aircraft. We're talking about isolated units of behavior that have like transient state and lifetimes. Maps really well to processes. It's an asynchronous message-based protocol, so we have message passing. There's a linear or serialized sort of state-based and time-based rules that apply to a lot of this stuff when the messages come in. And these are really modeled quite well with Gen servers and potentially even Gen State M, which I haven't tried yet. The receiver should be as stable and fault-tolerant as possible, because it's possible your app may actually be running on a Raspberry Pi that's mounted on your roof or in your attic, like I have at home, and I'm not going to get up there in the summer because it's like 130 degrees. And that's, do I need to say more? The beam. And peak air traffic can be like a fire hose. When I first wrote this application, I just let the traffic go straight through to my web browser, and it didn't work. We have things like GenStage for back pressure, and we also have ETS. We can do a lot of caching with that. There's a lot of value you can add. You can decorate the data with things that you use. Use like this address I was telling you about that's unique. You can use that to actually look up things like the aircraft's registration, and then from there you can figure out like who owns it, and it gets kind of creepy. But we have things like stream and flow and ETS that are great for that. And finally, my favorite, the beam is great for doing intense math needed for digital signal processing. I heard some hissing. That's what I was going for. Okay, maybe not so much. That's all right. We can outsource that. So the beam in Elixir is obviously great at delegating to external applications through things like ports, NIFs, and C nodes. And this is a fairly common pattern when you're interfacing with hardware on the beam. In this case, we need to talk to this RTL SDR dongle in order to configure it and start the radio. The application I built, Squitter, you can think of that as more like it's providing a high-level control and tracking functions, but it doesn't actually talk to the dongle directly. For that, I'm using a middleman. It's an open source application called Dump 1090. There's a fork called the Mutability fork, and it's probably the most effective open source ADSB demodulation software that's out there right now. And this is what's going to talk to the dongle using its drivers, and it's going to demodulate this byte stream that we saw into those 112-bit message frames. And it's going to hand that to our application. And then from that point forward, my application handles the rest. And just kind of give you a little bit of context, put things in perspective before I start showing you some code, I was just going to kind of go through like the overall high-level flow here. At the top, I have basically dump 1090, pushing those raw ADSB frames into our application where we will decode the messages. Once they're decoded, we know who they belong to. We will route those to a process that represents that particular aircraft. And then that particular process will apply the rule for whatever type of message it happens to be, update its state, and at that point will push a view of its state into an ETS table that is keyed by that particular address. From there, I have channels basically on a clock cycle, just ticking, looking at that ETS table and pushing that state out to the browser. And then I wrote a small Leaflet.js application that projects all this stuff onto a map. So the first thing we'll talk about is the decoding pipeline. Really nice thing about Dump 1090 is it provides a TCP endpoint that you can connect to where it'll just push to you those raw ADSB frames. And this is what we use basically as our first stage in a two-layer gen stage pipeline. And we basically just listen for those raw messages as they're coming in through that TCP connection. And so this is, instead of showing like all the code, I just ripped out bits and pieces, so I hope it's not too painful. But this is the handle info callback inside of that gen stage, that first stage where we're basically receiving the buffer, and because the buffer could at any point in time cut off, like right in the middle of a frame, we have to make sure that we split them and then capture what's left over, and then what we did receive, pass those on. A lot of times, a raw ADSB data is represented as just hex strings for whatever reason. So this first enum.map you see where I'm doing hex to ben is basically just converting that to binary. I do a couple of small checks on it just to make sure that weird things happen with these cheap little dongles. So just basically validate that it's valid. I tag it with an index as a kind of a logical ordering value. When you get like 50 of these frames in at the same time, when you're talking about a signal that aircraft is broadcasting like twice a second, it's very likely that you may have two messages from the same aircraft inside that particular buffer. So by tagging them with the index and then basically, tagging them with the time and then adding their index to it, I basically invented just a small way to keep them ordered. So those get dispatched basically immediately. The next stage is the next and last stage, I should say, is the decoding stages. And in order to make this performant and to maximize concurrency, I started up multiple stages of them, so they can all do their work in parallel. This creates a little bit of a problem, though. Now that the messages for the same aircraft, if they're coming in as quickly as they are, could be delivered out of order if they're routed through a different stage at the same time. So I needed a way to serialize the messages for those aircraft to make sure that they fit into a nice linear flow for that particular aircraft using their identity. And so that address is going to play a part in this. I basically take a peek at that 24-bit address that's in the header of every message, and then provide that as a hash value to GenStage, the partition dispatcher, during the init function on that first stage. Doing this means that basically that erlang.phash2 function is guaranteed to return the same integer for the same input. And then the second parameter on that phash2 call just basically restricts it to the range that's between 0 and then range -1. And for this case, it's the number of partitions that I'm using. And then finally, the aircraft processes themselves, these aren't gen stages. These are actually just gen servers. They're basically for each particular aircraft. When the message is delivered, if the process doesn't exist, it gets created before that message is dispatched to it. And I use a unique registry to track these. And I use it with the via tuple. Whenever it starts up, it just basically provides its address to this custom aircraft registry. So when these messages get delivered to an aircraft process, that's what this looks like. So I have this public dispatch function, takes an address, and it takes the message. And I basically call into a private cast function. At that point, the cast function calls getAircraft. GetAircraft, it's at the bottom here, basically just tries to start the child up for that processor, for that aircraft. And this is a simple one-for-one supervisor, and so this little syntax here is kind of weird, but if it already exists, it's going to come back and tell me it's already started. And if it hasn't, then it's just going to give me the PID. In both cases, I get the PID, so I just return the PID for both cases. And I feel a little bit like, I don't know, self-conscious about this because I feel like it's doing side effect-y type things, but if anyone else has any better ideas. All right, so then once I basically cast the message to the process representing that aircraft, that process basically just delegates it to its own internal handle message function. If that message gets handled, the aircraft is going to call this setReceived function, and that's actually going to update the aircraft's age, so we know that the aircraft is still active. And basically, what happens when these aircraft go out of range, all that happens is that you just don't get a message from them. So we basically have to just check to make sure that the aircraft is still active, and then track that timer explicitly, because it does give you a good indicator of how likely an aircraft is to go out of range as you start to see that age climb, and then it comes back down, and then it keeps kind of doing that, and it gets closer and closer to 60 seconds. And it's been fun to correlate that with on the map visually to see, because I've started to develop an intuition about where these aircraft go out of range, so I can visually verify that. But after the message is handled, so the state, the aircraft has likely updated its state. I call a build view function, and then it basically pipelines that result into a report function. Those two functions basically transform its internal state into a nice view of the state, and then push it into an ETS table. The only really weird thing that I'm doing in this case is for a report, I'm validating basically that we've received more than one message from this aircraft, and I'm also validating that we're within range. Basically, we have to validate that this isn't an aircraft that's like 400 miles away, because a lot of times that indicates that you're actually getting bad data. So I call this state change function on this state report module. What it does is just basically, it's a gen server, and it just basically inserts that row right into the table, into the ETS table. So obviously, one thing we don't want to do is when these aircraft go out of range, we don't want to leave their state behind. The process will automatically die because it's got that internal clock cycle going that figures out after 60 seconds that I need to just exit. But the ETS table, we have to have some way of cleaning that up. And this is something I'm kind of excited about because I just discovered it a couple weeks ago, but you can actually provide registry with listeners. And in this case, what will happen is if you give it a process name, registry will then send you register and unregister messages whenever something registers or unregisters against that registry. And this is kind of a painful slide. I know there's a lot of code on here, but essentially, the main thing to remember is that you also have to monitor the process because you're not going to get a notification whenever the process has like a hard crash. You're just going to get a notification whenever something registers and when it actually unregisters. And so in my code, I had to handle the register, handle the unregister, and then also handle the down message for when a process crashes. Cool, all right, so let's talk about nerves. I think the main takeaway that I wanted to bring to this talk about nerves is that, as I was building this application, I was trying to figure out, I've got to get this dump 1090 application into my code somehow. I got to make sure that, when this thing is pushed onto the Raspberry Pi, that it has dump 1090 somehow available. So I was going around asking people, should I use a Git submodule? Should I just clone the repo? Should I just, clone it right into my own repo and just keep, a copy of the source code around? And it was really bugging me, because none of those options felt like, a clean way to handle that. And then I found the build root docs. The build root docs are amazing, by the way. So I've listed here basically a 5 or 6 step process where you can actually add a custom package to build root in nerves, and it will build that software for you, and you don't have to provide it with the source code. You basically can give it you can even just give it a link to a GitHub repo and give it a SHA hash, and it will pull that exact version of that application down, and you give it instructions on how to build it, and then it's just magic. So the first step, I should mention that in this whole process of doing all this, I put out a custom system for nerves. If you wanted to get into doing STR and RPy3. So it's out there on Hex if you want to check it out. Right now, the only things that are in it is librtlstr, which are the drivers for the RTL software-defined radio dongles. I also put GPSD on there just because for what I'm doing with ADSB, GPS is a component of not only being able to figure out how far away the aircraft are, but it also enables you to do a little bit more efficient decoding of their positions if you're within, I think, 180 nautical miles. So having that available is something I'm kind of looking forward to integrating with my application, just to be able to get the site's location automatically without having to hard code that everywhere. So this is the first step. If you want to add a custom package to build root or to nerves, to your nerves build, what you have to do basically is provide a config.in file. You create a package directory inside of your custom system, and then within that, you provide another folder for whatever the name of your package is. And this syntax is a little weird, but I'm telling you, the docs for build root will walk you right through it. It just specifies dependencies. You can see here that this is a package I'm calling dump 1090, and I told it that it depends on basically a toolchain that has threads, and I told it to select the librtlstr drivers. Whenever this package is selected, then it will also select that, because dump 1090 needs those to be available. You give it a nice little description, and this will show up whenever you're keying through the kconfig menu like Justin showed this morning. And there's also a search component to that kconfig that makes it really easy to just find whatever you're looking for. The second step is probably at least the most intimidating looking. You have to add a makefile to your package subdirectory. And again, the build root docs are really helpful here. But this is what it would look like. And there are different type of packages. I think like if what you're trying to build uses CMake, it's a little bit easier. But in this case, dump1090 is just using a standard makefile. So that requires what's called the generic package. But even then, like I said, build root will walk you through it. I give it a version, and it can figure out just based on the type of site that I give it. If I'm giving it a hash, it'll just pull that particular hash down. You can also give it a tag, branch, whatever you want. You tell it the license. You tell it some of the dependencies as far as like libraries go for when it actually does call make. And then you give it kind of what the make command would be, and you tell it where you want the files to end up whenever it's installed. The third step would be you have to add a config.in to the root of your custom system, and all this is going to do is basically just include your other config.in. I don't know why. And the fourth step is similar to the previous step, where we basically have to include we have to include the makefile that we wrote. And so we have to do that from the top level directory. And I think it's because of the way that the nerves is kind of set up with using nerve system BR underneath. I'm not sure. And then finally, the last step would be that now that you've actually put your package into the build root system, like you have to select it. So this would be like your nerves_def config file. And then of course I couldn't resist adding step 6, profit. All right, so I kind of talked about, I guess, from the squitter side, where we're getting the data from dump1090 and then all the way up through the ETS side. Now, how are we actually going to get that data out onto the web? And so I kind of alluded to it earlier. We take the channels when they start up. They basically they look for, they send first of all, the JavaScript client sends a Roger message. And then once our backend channel here receives that message, at that point, it will send the first, basically, list of position reports that it has or state, I should say, for all of these active aircraft at this point. And the first one needs to have all the historical trackways built up too. So we don't want to send that every time. So if you see where I have state reports and then true, I'm just telling it to say, like, also include the position history. And then for all the subsequent requests, that flag is left out so that we just get like the current position. I call it the schedule report push function. It's on the next page. That just basically sets up a timer using process.sendAfter, and for every second, it will send itself a send report message, which you can see the handle info for that is at the top. And whenever it receives that message, it asks the ETS table for its reports, and then it just basically reschedules that message. So it's sitting there just on a clock cycle of 1 second, just getting whatever the current state is from ETS. I initially experimented with trying to get GenStage to go end to end between my application and then the web front end, and that's when I discovered that even back pressure sometimes, it's tricky, because if you want to rate limit this, you're effectively rate limiting for all of your clients at the same time, and I felt like I was kind of jumping through a few hoops trying to get it to be a little too dynamic when I could just do something like this, where I'm pulling out of an ETS table once a second. All right, so I want to kind of get into some demo stuff here. I'm doing a little bit of smoke and mirrors here. Like I said, the signal from my hotel room wasn't great, and so I'm actually pulling data off of adsbexchange.com, and I pulled from, I think it was 2 days ago. This is a look at my application. Basically, on the right side, we have a list of all the aircraft that are on the map, and this is a heat map that I added. so that I could see the trackways and the airways the aircraft are using. And it's kind of interesting. You can see right smack in kind of the middle is SeaTac, and then up above in the center-ish is Vancouver, and then even down towards the bottom is Portland and the high traffic areas. And then even to the east, I believe that's Spokane. If we zoom in on that, you can actually start to see very specific patterns. It looks to me, if I had to guess, that looks like a departure, hopefully. But it's right over the airport. All right, so I'm going to actually switch to the live application right now real quick before we run out of time. And I'm just running this in host mode. Guess I should probably turn off mirroring. So these range rings that you see, those are every 50 nautical miles. And this is about comparable to what I get at home with, I have a 26-inch antenna in my attic. So that, I guess that outer ring would be somewhere around 250 nautical miles. We can take a look at these aircraft, and the color coding system just represents altitude. Green is like the lower altitudes. Blue would be like your middle, kind of your 10,000 to 20,000 level, and then purple and bright pink would be like your 35,000 and 40,000. We can turn on all the tracks for the different aircraft we want. We can see, oh, sorry. You can see most of the aircraft that are nearer to the center of Seattle are at a lower altitude. This guy's turning around. And I can also turn on the individual position reports. So I'm using a leaflet application here that has really great polyline support, but it extrapolates between the points that it receives. But this allows me to kind of actually see, as the plane is reporting its position, I can see those individually. Anyway, there's a lot to this application. I had kind of skimmed through a lot of it just because there's so many, and I didn't even get to talk about the JavaScript part, but if you want to talk to me about it afterwards, like I'd be more than happy to do that, and thank you for your time.